So my buddy Steve has asked me to do a simulation study to see what the effect would be of the forces and pressures on his spinner at around a cruise speed of around 4,000 RPMs on this spinner assembly. The simulation analysis will be broken up into two parts. The first part will calculate the effect of the pressure loads due to the rotating air around the spinner at 4,000 RPMs, and then we'll go ahead and calculate the second part, which will be the effect of the stresses due to the centrifugal forces from the spinner rotating at around 4,000 RPMs. To start our flow analysis, we'll go to Tools in SOLIDWORKS, click on Flow Simulation, and we'll generate a project using the Flow Wizard. Give it a name. We'll call it Steve 1. Unit system, we'll use English units. We'll also tell the software this is an external calculation, which means that the air will flow around the spinner, and also that the air will be rotating around it at around 4,000 RPMs, which is our cruise speed. For gases, we'll use air. The software will then create what's called a computational domain, which is the area around which the spinner will be enclosed and where the calculation will be done. And of course we can adjust the size of this boundary to make it a little bit smaller and a little bit more realistic. Once the project has been created in SOLIDWORKS Flow, a feature manager will appear, just as you would see in SOLIDWORKS. The next thing I'm going to do is to create what's called a rotating region. The rotating region simulates the air rotating around the propeller at 4,000 RPMs, similar to what you'd see maybe in a wind tunnel. We have this rotating region, and now we're going to go ahead and create the actual rotation of that region in the flow program. So we'll pick that region and we'll tell it to rotate it at 4,000 RPMs. In this particular case, it's a counterclockwise direction. That sets up my complete input for the analysis. The other thing I can do is define goals. Goals are nothing more than the parameters that you're interested in calculating to display after the calculation is done. And that's what I've done in this particular area here. So we're ready to run the software, so we'll go ahead and do that and come back and then show you what the results are. Once the analysis is completed, we can show the results in a variety of forms, via tabular form or in plot form. So what we'll do first is we'll look at a couple of plots of the velocity in different planes. Let's do that. Here we see the velocity contours showing the velocity moving in a counterclockwise direction along or around the propeller or spinner. It's around 17 miles per hour. Let's show another plot of that too in a different direction. You can see the perpendicular plot, and you can see how the velocity changes as we move from the front of the spinner to the back of the spinner. Increasing the velocity significantly as we move through the spinner is what you'd expect. That's one type of plot we can show. The second thing we can show is the surface plot of the pressure distribution on this spinner. You can see there's a variety of different pressures along the front blades and along the back blades. However, the variety is not that large in deviation, so I don't expect to see a lot of stress generated from this air moving around the propeller at 4,000 RPMs, but we'll see when we get to the stress calculation. That's our second type of plot that we can show. Finally, we can show a trajectory plot. And the trajectory plot will give us a complete picture of what's happening as the air moves from the front of the spinner to the back of the spinner. And we'll do a little animation on that and show you what's going on there. And you can see how the velocity increases as we get to the spinner, and it gets significantly higher as we move to the back of the spinner. And you can see it revolving around the front of the spinner in that counterclockwise direction. So we'll stop that. The next thing we're going to do is, since we've generated the distribution of pressure and forces now due to the flow analysis, we'll go ahead and import that into a stress calculation and find out what the effect is by calculating the final stresses and the displacements. The final step in the analysis is to take the pressure loading generated from the flow analysis and import it into a stress calculation. Plus we'll also include the centrifugal effects of the spinner rotating at 4,000 RPMs. I've set up a simulation stress analysis study, And we're using a material of 10% glass-filled nylon, which is typical of these RC spinners. I'm fixing the back right here. I'm including the loads from the pressure calculation in the flow analysis right here. And I'm also including a loading of 4,000 RPMs for the centrifugal analysis in a counterclockwise direction. So let's go ahead and run the analysis and see what happens. Okay, let's take a look at the results. We'll first show the displacement plot. The displacement shows a movement of around 1/10 of an inch, mostly in the forward direction, which is probably what we'd expect because the propeller or the spinner is pushing the model airplane forward and giving it some thrust. So that's not a very large number, so that looks pretty good. Let's look at the stress result. The stress result shows around 3,000 psi along near the edges of the blades of the spinner itself. Typically for a material like this you would expect a yield point of around 8,000 to 20,000 psi, so we have plenty of safety margin in this spinner. So at 4,000 RPMs we're in great shape, and Steve can probably run his RC plane up to a much larger speed and not have his spinner break. So I think you're in great shape, Steve. Hopefully you enjoyed it.